Good morning. I want to make you guys a series of videos to guide you through understanding LOL diagrams and solving for unknowns in energy problems. So this is part one where we're going to focus on just making a qualitative LOL diagram. You're thinking, what's an LOL diagram? Well, it's this diagram that's sitting right here. Open it up. It looks like a L was the first bar graph, O in the middle, and then L a second bar graph. The first L and the last L, those are bar graphs, as I said, and that's where you're showing relative levels of different forms of energy within a scenario. The O, which I've got like my box highlighted, but the O is just a place for you to keep track of what items are in your system versus what items are not in your system, because that's going to matter when we start incorporating work into our problems. So I've got a fake scenario here just to show you, and that is a slingshot is used to launch a rocket into the air. Friction is negligible. Cool. So slingshot launched a rocket in the air. So if I'm going to visualize that, I'm going to, now we'll just write it out first. I know that since there's a slingshot, that is an elastic material, got like a rubber that stretches. So that means I'm definitely going to have some spring potential energy. And then it says it's launched into the air. I'm going to go ahead and pick the point where the rock is at the highest to be my second snapshot, which means since I have height, I'm going to have gravitational potential energy. If I picked a different snapshot, such as maybe halfway up the projectile path, then I would account for speed. But because I'm going to pick that top path for velocity of 0, I don't have to account for speed or kinetic energy. Since friction is negligible, I don't need to think about thermal energy in this problem. So we're just going to leave it at that. Great. So we know we need spring potential energy. We know we need gravitational potential energy. Let's make our LOL. This was just qualitative, which means I'm just going to be kind of drawing general bars and hope that it all adds up. Remember that energy is conserved. So whatever energy I have on one bar graph, I have to have on the other. I can't have energy disappear without being able to account for it in some way. So got to focus on that. First things first is we're going to write the objects that are in our system. So we have a rock. We have a slingshot. We also have the Earth. For most of our problems, Earth is going to be in your system, so make sure to always write Earth. Earth is what allows us to have that relative height of 0 when stuff's on the ground. So we can say, oh, if it's above the ground, then there is a height, and that must mean there's a gravitational potential energy. Because remember that it's Earth's gravity that's pulling stuff towards the ground. That's where the energy for objects to fall comes from. Great. So rock, slingshot, Earth. Just leave it at that. So I said I started off with some spring energy because we're stretching back. So I want to make a bar for that. I'm just going to go to shapes, make my life easy, and I'm going to say, oh, this much. I have this much energy. Great. Then we said our second snapshot is at that highest point. So I am going to, actually, you know what I'm just going to do? Since I know all of my energy has to be converted because energy is conserved, I'm just click copy paste. And since it is all stored in the height, I'll just put it right there. Now, I do want to notate that I have thought about the fact that there are no other forms of energy. So I'm going to say that originally there is no height because it's like stretching back. So I'm going to just use, I think there's an X shape in here that's really easy. I think it's in equations. Yeah, so if I go to equations and I use the multiply symbol, then I can make myself an X that I can just copy paste. So I know there's no gravitational potential energy because there's no height initially in my scenario. I know that there's no kinetic energy because it is not moving originally in my scenario. And I know at the end, we pick the point where its velocity is 0 on the path. So we say the kinetic energy is 0. The slingshot is no longer being stretched. So we have no spring energy. And then we said that friction is negligible. So we're not going to have any energy converted to thermal energy. That's basically how you make an LOL diagram. If I had a slightly different scenario, let's say there was some height beforehand, then all I would need to do is I would need to account for that in my bars. So I can't just say, okay, that I've got this much energy in gravitational potential energy, this much energy in spring energy, and then only half of that amount of energy left with my gravitational. These two bars added together have to equal this one. Energy is conserved. So if I had a different form of energy, say there was some height beforehand, let's say there wasn't that much height, then I'm going to have to subtract that much from my bar. It's okay to guesstimate. So that when I add these two bars together, I get this bar, okay? This is just a way for us to map out our energies and what the forms they start with and what forms they end with, because we're going to use this diagram to form conservation of energy equations. You can hear me say that a lot this unit. So this is just a quick overview. Our problems are going to vary a little bit, but this is just to show you kind of a basic how to make one. All right, in part 2, I'm going to show you how to take this from qualitative to quantitative. If I ever can figure out